Alright guys, so this is the magnetic field coil out of a DC electric motor, and you're probably wondering, why do I have it in the saw and why am I cutting it? Well, as you know, it's always a rush job and we need to get this thing back to them right away. You can see how jam-packed these wires are inside of this coil, and I need to put all the same amount of wire back in, and I need to make everything fit exactly as it fit before. If we make this coil a little too big or a little too short, it's going to change our resistance, it's going to change the performance of the machine. I ended up counting 564 turns inside of this coil. I made a jig so that I could make these coils. And the resistance number that we're shooting for these coils was 7.1 ohms, and as you can see, it's dead on. But I can't just slap this coil back in the machine like this. We're going to have to go ahead and wrap this, protect this thing, and we need to shape it because it needs to fit, like I said, exactly as it fit before. So we'll use some different types of insulation materials, and I do have to keep constant tension on this. If I let go just even a little bit, it's going to unravel a couple, and I'm going to have to pull back and restart what I was just doing. As I'm going through this and tying this wrap around this coil, I have to constantly be beating the coil with a rubber mallet that you can kind of see on the right there. It's rubber on one end, plastic on the other, but we have to constantly be shaping this thing because we need it to be uniform and we need it to fit exactly back as it did. There's 4 of these field coils inside this DC electric motor, but we're not only going to repair one of the field coils. Even if only one was bad, we will repair all 4, rewind all 4, because if one was subject to an overload, they were all subject to an overload. This is the pull piece that coil is going to sit on, and just like our 3-phase electric motors, you can see that this is made up of individual laminations so we can reduce those eddy currents, and I would bet that those pins going through that are going to be a non-ferrous metal as well. Otherwise, they're going to get extremely hot and melt, and nobody likes melted pull pieces, and we also don't like dirty pull pieces, so we're going to throw these in a sandblaster. We'll clean up each one of these individually, and as I said, we weren't replacing just one, we're replacing all 4. So once I got 4 identical 7.1 ohm 564 turn coils, we can get ready to start putting these back in our stator. So the empty spots you see in between these inner poles are where our field coils are going to go, and we also have these copper shims inside here. It's really important that we keep those where they were or substitute them for a different material. It's extremely important that we maintain air gaps in these machines. If we start trying to pass magnetic flux through a larger air gap, we start to have major problems between balance or current. Without going too deep into that, here is our stator with our new field coils inserted. Now we are going to dip this in our VPI vacuum pressure impregnation tank, so we're going to use a Class H varnish on that. We do have another DC motor in our shop as well, so you can see our field coils here and our inner poles again. So those inner poles are there to essentially distort the flux coming off the armature that is bending our flux coming off of our field poles. These are really cool machines. Like I said, we don't do a lot of these, and believe it or not, for the size of this is 125 horsepower. The one that I just wound the field coils for was 71 kilowatts, I believe. And I know someone's going to ask, how does Tesla make such a small motor and output 600 horsepower? Well, these things are going to output their rated horsepower 24/7, 24 hours a day, 7 days a week, 365 days a year. Cheers, guys.